Here we have another instance where a word which has a certain meaning in regular everyday English has a different meaning in the context of linear algebra. When you think about independence, well, if you're American, maybe you're thinking of Independence Day, or if you like watching movies and so on. But maybe another common meaning is that of being independent of your folks and living an independent life and so on and so on. Well, in linear algebra, there's nothing like that. What we're talking about is vectors and not people. That may be a little bit disappointing, sorry about that, but we'll have to stick to what the course has to say. So, vectors. First of all, in order to introduce to you what the concept of linear independence is, I need to refresh your memory on some things that we saw earlier on. And the idea is the following. Let's say that we have a bunch of vectors, so v1, v2, and a whole bunch of other ones, and then some vk. So we have k vectors with k some number. You may remember that one of the things we can do is take each one of these numbers and multiply them by some coefficient. That's scalar multiplication. At this point, we have a bunch still of vectors, and we can add them up and obtain in this way another vector, which, as you may recall, is called the linear combination of the original vectors. So let's call this new vector vk plus 1. We could have called it w or u or whatever you want. It's just another vector which is a linear combination of the original set v1, v2, vk. So far so good. Now what we're going to do is something algebraically very simple. What I'm going to do is I'm going to take the left hand side and write it down, and I'm going to take that vector on the right hand side, which I said is a linear combination of those on the left, and move it to the left hand side. So in that way, I'm going to move it to the left, and of course that means that I'm going to have to subtract it, but instead of simply writing a negative in front of it, I'm going to write as plus -1 times the old vector. Well, if I moved, by the way, you'll see in a minute why I'm doing that. Now, if I move this vector from the right hand side to the left hand side, what am I left with on the right hand side? Well, of course, I'm left with 0. So what I have is that if I've constructed a linear combination of my original set of vectors v1, v2, vk, and if I move that to the left hand side, I end up with what you think, when you think about it, is just another linear combination of v1, v2, vk, and vk plus 1, which altogether come up to be the 0 vector. Notice also one more thing. If you look at all the coefficients in front of those vectors and you add their absolute values, you end up with something which is definitely positive. Why? Well, with certainly the absolute value of -1 is 1, and then all the other coefficients, c1, c2, ck, the worst they can be is just 0, in which case we just end up with 1. But if they are anything other than 0, then their sum will add up to something even more. And therefore, what we have done is we have constructed a linear combination of a whole bunch of vectors, which actually turns out to be 0, through coefficients whose sum of absolute value is actually greater than 0. Okay, so keep that in mind. It may look like a silly thought at the moment, and you maybe wonder, where is he going with that? Well, I'm going to show you in a minute. Just don't worry. Also, notice that if I start from the same vectors as I started before, v1, v2, vk, and I multiply each of them by the number 0, the scalar 0, and then I add them all up. And by the way, if you think that I'm neglecting vk plus 1, okay, let's throw in vk plus 1 as well, multiplied by 0 as well. What do we end up with? If I take this linear combination, well, again, we come up with the vector 0. But this time it is obtained as a linear combination of vectors, each of which has been multiplied by 0. And you might say, well, this looks like the class of really stupid things. It looks like a very simple concept, and it is, except that it's going to become very important and very useful in a few minutes. So hold on with this thought. We have a linear combination. We moved the right hand side to left hand side. We end up with a linear combination that equals 0, and such that the sum of the absolute values is greater than 0. But on the other hand, we can also obtain 0 by using a linear combination where the coefficients are all zeros. So their absolute values all add up to 0 as it is. Alright, so what we're going to do is we're going to take these two very simple basic ideas, we're going to generalize them, and we're going to come up with this idea of linear independence.